Hello and welcome. This is SFU Math 2 to 32. It's Brenda speaking. This is section 11.11, coordinates with respect to a basis, and this is the final lecture for the fall. Well, it doesn't matter. It's the final lecture for Math 232. Okay, so what is our final thing that we're going to talk about? We're going to talk about um, the coordinates of a vector with respect to which bases you are telling the person the coordinates of the vector with respect to. Okay, so I'm just going to motivate this by way of an example. So we have a vector here. Here it is, 0, 3. And we want to find the coordinates of that basis with respect to the vector, with respect to these two vectors, v1 and v2. Okay, so what we really have right now is we have that v1, sorry, not v1, v, this guy here. We have it. We sort of have it implied when we have these two coordinates here for v. What we really are saying here is that v is equal to 0 times e1, the standard basis vector, plus 3 times e2. That's what we're actually saying. We don't say it like that. We capture that information by just saying it's the vector with components 0 and 3. But really, those are the coordinates. Those are the scalar multiples of the standard basis vectors that we use. Okay. Now, instead of doing that, we want to position v with respect to two different basis vectors, these guys, v1 and v2. Okay, so effectively what I want to do is we will want to be able to write v as c1 times v1 plus c2 times v2. And so we've done this lots of times in a variety of different guises. So we want to take the vector v, 0, 3, and write it as a linear combination of v1 and v2. And that gives me two equations and two unknowns. 2c1 minus c2 is 0, and c1 plus c2 is 3. That tells me that c1 is equal to 1 and c2 is equal to 2. So I can write 0, 3 as 1 times 2, 1 plus 2 times minus 1, 1. Okay, or I could write it this way. 0, 3 is equal to 0 times 1, 0 plus 3 times 0, 1. Okay, so when I choose to do something like this here, I will indicate that this way, that B is this here, 1, 2. So this is the vector v with respect to the basis b is 1, 2. So I'm capturing these two constants here, this one and this one here. In the same way here, if I consider, let me just name this, let S be this thing here, S be E1 and E2. I could write here, and it's correct to write, that V with respect to the basis S is 0, 3. So that's been our assumption all along. We have just not indicated that. This is a little bit like we say, we have 4 little pebbles on the ground like that, and we say, oh, that is, somebody says to you, how many pebbles are there? You say there's 4. And then if you were you could say, oh, it's 4 in base 10, or you could say it's 1, 0, 0 in base 2. And if you just happen to say 4, people assume, oh, well, the normal thing to do is to do it in base 10. They assume you mean this. Okay, but you actually are referencing the way you're going to where you're going to talk about that number with respect to a base. And really here what we're doing the same thing. We're saying that these coordinates here are with respect to some basis. And so far we've been basically referencing them with respect to the standard basis. So we don't indicate that. But now when we're going to have different bases, we're going to have to indicate to which basis are we referencing them. Okay, so again, let's just draw a picture of what's going on here. Like that. We've got E1 here, and then we've got E2 here, like that. And then we've got this vector V, which we know is 0 of E1 and 3 of E2. So this number right here is 1, 2, and then here's 3 right there. And our vector V is formed by taking no E1s and 3 E2s. So it's right here, like that. Okay, we can then also take a look at where the vectors V1 and V2 are. So V1 is at 2 and 1 right here. So let's just get a different color for that one. So V1 is right here, V1. And where's V2? V2 is minus 1, 1. So here's minus 1 and then 1. And so there is V2 right there. And so now I'm being told, oh, the other way that you can get over here to V, I'm just going to label this so we're confused about what we're doing. We can, instead of going no times on E1 and 3 times on E2 to get up to V, we could instead go, well, what are the numbers? 1 time on V1, so we would go here, 1 time along V1 like that, and then we would go 2 times on V2. V2 is this guy here, so we put it here, V2, V2. Let's do a better job there with the drawing. We're going to end up here, V2 and V2. So we go 2 times V2 and we end up at the same spot. V is unchanged. In one way, we're just telling you how to get there in 2 different ways. One way, you walk along V1 once and then you walk along V2 twice. And then if you don't want to go that way, then we change the basis. And we say that's fine, you don't want to go that way, then instead don't walk along E1 and walk 1, 2, 3 times along E2. You end up at the same place. Okay, so basically V is being expressed in 2 different ways with respect to B and with respect to S, but it's the same vector. Okay, that's what this is. That's in fact the whole point of this lecture, is to recognize that we can do it. What the notation for doing is, and that we're not changing the underlying vector. We're just changing which basis we're stating it relative to, and then we can change from one basis to another. That's it. Okay, so here's the definition. We've got a basis right here, and we have a vector that is a linear combination of the basis vectors. And we notice that all we need to do is to identify which vector V is, we need to just capture those constants. And so we would say then the vector W with respect to the basis are those constants, those guys right there. And then what we mean by that is that V is A1 times V1, the first basis vector, etc., like that. Okay, so we call that the coordinate vector for W with respect to V. Okay, and if we put it in a column and put the little matrix indication on it, we call it the coordinate matrix for W with respect to B. Okay, let's just take a look at this. Find the coordinates of W. There it is, 1, 2, 3, with respect to the basis V1, V2, V3 given there. So what I want to do is figure out how do I represent 1, 2, 3 as a linear combination of these three basis vectors. Okay, so this is our usual problem. So what we have to do is form the augmented matrix. There it is. And row reduce. Oops, two. And just changing that third row there. There it is. I've row reduced it. And I can see from this thing here, I can make some headway. I can see that C3 is minus 1/2, C2 is 5/2, and C1 is 1/2. Okay, so then I can check that. 1, 2, 3 is equal to 1/2, 2, 0, 0, plus 5/2, 0, 1, 1, minus 1/2, 0, 1, minus 1. Okay, and I should see, so I mean, on that first row, that should be that 1/2 of 2 plus 0 minus 1/2 is equal to, what happened? Hang on. 1, 2, 3. I should be getting a 1 there. Hang on. 1, that is 1. Did I write this down? Yeah, that is 0 minus, oh, sorry, it's 0. God, what I did wrong here. This is 5/2 times 0 minus 1/2 times 0, not plus 0. Okay, so that works out to be 1. Oh, so things are haven't at least not yet gone haywire. Let me just check the next one since that happened. 1/2 times 0 plus 5/2 times 1 minus 1/2 times 1. That is 4/2. That's 2. Okay, so that's what I would expect. I mean, there's the 2 right there. Okay, so I then write this way. The vector W with respect to the basis B is 1/2, 5/2, and minus 1/2. Looks different from this. Okay, that's with respect to the standard basis vectors. Okay, to emphasize that point, we want to find the coordinates of this vector in Rn with respect to the basis of standard unit vectors. I mean, these guys are so nice to work with, right? So the basis of the standard unit vectors is going to be this here, 0, 0, 0, enough zeros like that. And then the next one, 0, 1, 0, enough zeros like that. And then you keep going, and 0, 0, and you get 1. Okay, those are the standard unit vectors. W is a vector in Rn, looking like this, W1 dot 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 Wn. And W looks like this, W1 times E1. This here is E1. This one here is E2. So that's W1 times E1 plus W2 times E2 plus dot 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 plus Wn times En. Okay, so W with respect to the standard basis vectors is W1, W2, Wn. Okay, that's exactly what we have written here. All along we've been doing this, and we haven't really thought about it too much. This is like that equivalent thing saying here and then writing nothing here and assuming, okay, that means nothing is there, so that means 4 in base 10. I mean, we could have 4 in base 7 or something like that. Whatever, 4 in base like this. But if there's that assumption of if you don't say anything, what basis is it referenced to? Okay. Now, if the basis that you want to reference your vector to is an orthonormal basis, then it is easy to compute without doing Gaussian elimination. It is easy to compute the components of W reference to that basis. And you do that in the following manner. You take the vector and you dot it with the first basis vector, and then you take that that is the scalar amount of V1 that you want. And then you do the same thing for all of them. Okay, so those are all the dot products going across there like that. W dot BK times BK. Okay, so all these guys here are scalars. Those are all scalars. And those are the amount of each of the orthonormal basis vectors that you need. Okay, so then I've written it out like this in longhand, but then in order to write it out in this notation where we say the coordinate vector for W with respect to B, the basis, then the actual scalars are what I put in here, and those scalars, as we see above there, these are the scalars. That is scalar 1, next scalar like that. So these are the components of W reference to B. Like that. Nice thing about the orthonormal basis here is we're computing these numbers here by computing a dot product rather than solving a linear system. Okay, here comes a theorem. If B is an orthonormal basis, so we careful about what we have here for a k-dimensional subspace of W, and if we've got these three vectors in W, and they've all got their own coordinates reference to B, then it is the case that the norm of W will be the norm of W reference to B, and that the dot product will be the same as the dot product. The dot product of UV is the same as the dot product of U reference to B with the dot product of V reference to B. Let's just see an example, okay? In 2D, no less. Big surprise. Okay, so let's take a basis B that looks like this. This is an orthonormal basis, 1 over root 2, 1 over root 2. That's one basis vector. And then the other one, minus 1 over root 2, 1 over root 2. There we have an orthonormal basis. And let us just choose some vectors. So I'm going to choose U, and I'm going to make it this way. I'm going to take U as root 2 times B1 plus 3 root 2 times B1. So that's going to make U this vector here. So U is sorry, this is going to be B2. U is in the space spanned by these two basis vectors. There's a linear combination of them. So U is, what did I get here? Root 2 times, let me just do it. Root 2 times B1, 1 over root 2, 1 over root 2, plus 3 root 2 times minus 1 over root 2, 1 over root 2. Okay, what does that work out to be? U works out to then be, I get 1 plus, you get 1 minus 3 is minus 2. And then I get 1 plus 3 is 4. So there's U. That is U. This is referenced to the standard basis vectors. Okay, I'm going to do the same thing. Get another vector V. I'm going to take V as minus root 2 B1 and plus 1 over root 2 B2. And when I make that calculation, I find that V is this guy here, minus 3 halves minus 1 half. Okay, so let me just restate what I've got. I've got u equal to minus 2, 4, and v equal to minus 3 halves minus 1 half. I've got u referenced to b as root 2, 3 root 2, and v reference to b as minus root 2, 1 over root 2. Okay, they're in the same place, of course, on the coordinate plane. Okay, so the theorem here is telling me that if I take u dot v, let me just do that, u dot v, that will be minus 2, 4 dot, minus 3 halves minus 1 half. That is minus 2 times minus 3 halves plus 4 times minus a half. And that comes out to be 3 minus 2, which is 1. Okay. Now I can take over here, or maybe below, in fact. So now I'm going to just calculate it the other way. I'm going to calculate it this way. I'm going to take u reference to b dot b reference to b, and that is going to be root 2. So that's these guys, these two here, root 2 times minus root 2, and then 3 root 2 times 1 over root 2, and that comes out to be minus 2 plus 3, and voila, it's also equal. So that is what a theorem is telling us. When you're calculating a norm or you're calculating a dot product, it doesn't matter to which basis the vector is referenced. Okay, now the main point of this lecture is that we can change the basis. So sometimes if you're trying to solve a problem, you may wish to change the basis so that it's more intuitive what you're looking at. Sometimes it's not as appropriate to reference to the x and y axis. You want to maybe rotate the basis somehow or something like that as per the physical situation that you're dealing with. So we have the ability, so we want to have the ability to change the basis. So what we have is we have a vector w, we have a vector w and rn, and what we're going to do is try to change the basis from some basis b to another basis b prime, and we got to ask how can we do that. So we've got the vector w referenced to basis b, and then what we want to do is reference that same vector to the basis b prime. So I am going to say here, I'm now looking at the basis vectors here of b, and I'm going to say that, what does this mean? I just want to make sure we have this whole thing here correct. If I take a look at this vector, v1, what does that look like reference to b? It looks like this, 1 times v1 plus 0 times v2. Right? It is v1. Okay, similarly, the second vector, reference to the base of which it's a basis vector of, looks like this, 0 times v1 plus 1 times v2. Okay, now, if I take v1 and I reference it to basis b prime, it's going to have some two components, a and b. And similarly, that will happen for v2. It will be two different components. v2 reference to b prime will have two components. They will be called c and d. Okay, and that means really that v1, the vector v1, is a times v1 prime plus b times v2 prime, and that v2 is equal to c times v1 prime plus d times v2 prime. Okay, I'm going to take I'm trying to see how to change W. So I'm going to take W referenced to B to be K1 and K2. That means W looks like this. K1 times V1 plus K2 times V2. Now I want to figure out how can I reference W to V1 prime, V2 prime. So W is equal to K1 times V1. But V1 is right here. V1 is A V1 prime plus B V2 prime. And then it's going to be K2 and then V2. And V2 is right here. C V1 prime plus D V2 prime. That means by just arranging the terms and collecting up these two terms together, that means that W is equal to K1A plus K2C times V1 prime plus K1B plus K2D times V2 prime. That means that W reference to B prime is K1A plus K2C and K1B plus K2D. Then I'm going to rewrite this like this. A, C, B, D, and multiplied by K1 and K2. Okay, and that is A, B, C, D times W referenced to B. And you see what this is here. This is V1 referenced to B prime, and this is V2 referenced to B prime. These guys right here. Let me just circle those things to see what's going on here. We got here AB, and then here's the AB, like that. Okay. And then the other one is here, CD, CD. And so this is a 2x2 example, but this is how we basically are going to change bases. Like what we have here is on this side we've got W reference to B, and over here we've got W reference to B prime. So what we have to just do is figure out how to reliably find that that matrix, and we see how to do it here in the 2x2 case. So let's just get the theorem out here that is going to tell us how to do this. So if we have a vector and we've got two different bases, and we're going to maybe call B here the old basis and B prime the new basis, and we want to change the coordinates. So we have a vector W, and we have it already related to basis B. We want it related to basis B prime. Then we want to be able to find this matrix, which changes the basis from B to B prime, and call that the transition matrix. And what we see is that it is the columns of that matrix are the basis vectors from B reference to B prime. And we call that the change of coordinates matrix. It is the case that both of these matrices are invertible, and they are inverses of one another. I mean, this is in some sense should be a little bit unsurprising, because if you change from a basis B to B prime, then you can change back from the basis B prime back to B. So you can go backwards. That's what this is telling us. We can go back. Okay. All right, so let's see what our procedure is going to be for doing this. We're given two bases, B and B prime. We're just going to point out just as we start this up here, these vectors, for both of them, it doesn't matter, but these bases, these are linearly independent. Why are they linearly independent? It's a basis. B prime is a basis. Okay, so that means the vectors in there are linearly independent. Okay, so what we can do is we can consider Vj from this vector here, Vj from B, and what we want, Vj reference to B prime. Okay, so that is, we want to see this. Vj equals C1 V1 prime plus C2 V2 prime plus dot 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 Cn Bn prime. Okay, I'm going to let x be equal to all these constants. C1, C2, dot 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 Cn. Okay, then it is the case, just like it was in the smaller dimension example earlier. We have here V1 prime, V2 prime. So these are the vectors as columns. Vn prime, x is equal to Vj. Okay, which means, of course, we can solve the linear system by row reducing the augmented matrix, V1 prime, V2 prime, like that, Vn prime, and then we have the there with Vj there. Okay, like that. Okay, so what we do is we row reduce that down, and we'll get to the place where we have I, and then the last column will be Bj B prime. Okay, so now what we've done with this little setup is we've done one of them. We did Vj. So we have how many? We have n of them. We've done one of them. We've done the jth one. Okay, so let's note that here. This is one of them. We want to do j equals 1 to n, and we want to do them all at once. Like, who's going to want to do this n times? Nobody. So maybe not even wanting to do it once. Okay, but certainly once is better than n times. Okay, so this is how our procedure is going to work. To compute this matrix that we can then use for changing bases, we're going to form this matrix where we have as column vectors, we have the basis vectors of the new basis, and we have the vectors of the original basis. And then we're going to reduce the matrix all the way down, the full reduced row echelon form until we get to I. And then on this side, we will have the matrix that allows us to do a change of basis on any vector that we like. Okay, so the idea here is in sort of like graphical form is we've got the new basis, that is B prime, and we put that together with the old basis, B, like that. We do row operations, and we get down here to I, and we then have here what we want. And then we can use that to change the basis of any vector that we want. Okay, let's take an example. Okay, we are going to find the change of coordinates matrix from B, which is the standard basis, to B prime, where we're given the two basis vectors for B prime. And then we're going to attempt to find the coordinates of a vector with respect to that new basis. Okay, so let us just remember E1 is 1, 0. E2, I'm just going to show you what the answer is as we get going, and you'll see how this works. E2 is 0, 1. So it is the case, that is our old basis, our original basis, however you want to look at this. The key is to put the new one here and the old one here. That's the old one. The new basis, B prime, this is the new one, that looks like this, these two vectors, 2, 1, and minus 1, 1. Okay, so our vector V, this guy, V, which is 1, 1, looks like this. E1, well, 1 times E1 plus 1 times E2. Okay, so the vector V reference to the standard vectors is 1, 1, just as we've said. Okay, now, before I actually set up the matrix, I'm just going to actually solve the problem for myself so I can see where I'm going, because it's a 2 by 2 case. I can do it in my head. So V is equal to 1, 1. I want to know, what does that equal? That is actually equal to 2/3 times 2, 1 plus 1/3 times minus 1, 1. Doesn't matter if there's a methodical way of doing this, but if you can see this, then you're like, okay, you can see what that is. I mean, that is equal to 1, 1. The top row is like 2/3 times 2, 4/3 minus 1/3 is 3/3, that's 1, and then 2/3 plus 1/3 is 1. So that's 1, 1. So I would then write here B reference to B prime is 2/3, 1/3, like that. Okay, that is where we're going. Now, what I want is the matrix to do that. I want to be able to compute this guy by doing multiplying this guy by a matrix. Okay, so how do I come up with that matrix? I take the basis vectors for the new basis as columns. I take the basis vectors for the old basis or the original basis as columns, and I row reduce. Okay, so I'm starting up the row reduction. Let's use the symbol I normally use. Here we go. It's the row equivalent here to, first thing I'm doing is dividing that first row by 1. All right, and then I am taking row 2 minus row 1. So this guy's staying the same. Row 2 minus row 1. And then let's keep going. Row 2 minus row 1. Then what I'm going to do, multiply row 2 by 2/3. Okay. Okay, and then I'm going to take row 1 plus a half row 2. There it is. So what I have then is the transition matrix right there. I've called that, well, what have we been calling that? That is going to be PB to B prime is going to be this guy here. 1/3, 1/3, minus 1/3, and 2/3. There it is. Okay, now I had my original vector V reference to the original basis as 1, 1, and I want to know what is V reference to B prime. So I take, we already know the answer. Let me just get the answer here. 2/3, 1/3. We actually figured that out, but let's pretend we didn't know that, or it's a much more complicated example. So what I do is I take this guy, 1/3, 1/3, minus 1/3, 2/3. I multiply by 1, 1, and I get 1/3 plus 1/3 is 2/3, and I get minus 1/3 plus 2/3 is 1/3. So this here is 2/3, 1/3. That's tick, yay, it worked. Okay, so but now at this point, if I have some other vector, let us see I have some other vector. Let's not call it V, it's confusing. Let's call it W. and that is reference to B. Who knows what it is? It looks like this, 2 minus 1. And then I want to know what is W reference to B prime. What is that? Then what I do is I take that same matrix, 1/3, 1/3, minus 1/3, 2/3, and I simply multiply by this next guy, 2 minus 1. And I get here, let's see, 2/3 minus 1/3, that'd be 1/3. And then I get minus 2/3, I get minus 4/3. Well, then I put this here, 1/3 minus 4/3. Okay, so now I can do as many of them as I would like. So that is how you take a vector that's referenced either to the standard basis or to any other basis, and you transform it into being represented, transition it to be represented by with respect to a new basis. That is the point of this lecture, that you can do that, and this is how you do it. Okay, folks, that is it. No new material after today. This is everything for the semester, and yeah, a couple of weeks to go and we'll be done. Thanks very much. Bye.